Okay, so we're going to look at problem 355 from the book. This one you have this frame structure, and you have it's hinged at points A and D. So right here and here, and it's basically saying that you have some cables pulling on it. And so knowing that the tension in the cable is 450 newtons, determine the moment about the diagonal AD of the force exerted on the frame by portion BH of the cable. Okay, so we're just going to gratuitously ignore that one. So what we're saying is there's a force going off here. Okay, and that's BH. And that is putting a moment about this diagonal. So what in the world does that mean? So let's talk about that for just a second. So what that means, I mean, this is clearly one of those problems that this unit right here, this whatever this is called, this frame, it's going to be able to rotate around this axis, around that AD axis. Okay, so we're saying by putting on this force in this direction, how much of that force is going to make it rotate around this axis? So that's what it's asking. So the way the book does this is they do it with the triple product. I'm not a big fan of the triple product. I'm not opposed to it. It's just that I think you're hiding a step that makes it a little more complicated. So instead, I'm going to basically do this. I'm going to say, here at point A, there's a moment, and that moment's a vector, right? So you have a r cross f, so you're going to have some moment vector in some direction, who knows? And how much of that is in that axis? That's what I'm going to be looking for. So I need the moment at A, and it's going to be r cross f. That's what moments are, always, right? The moment at A is r cross f. So what is r? Well, r in this case is going to be r from A to B is simply going to be 0.5 in the I direction and nothing in the J or K direction. Okay, and what is F? Well, F in this case is the force BH, which is the magnitude of BH, which is given here as 450. So 450 times lambda from B to H. Okay, so that is, I'm going to come up here, do it here. So you have 450 times, okay, from B to H, you have in the x direction, you're going from 0.5 to 0.875, so plus 0.375 in the I direction. In the y direction, you're going plus 0.75 in the j, and in the k, you're going minus 0.75. You're going back this direction, 0.75. Okay, but that's not lambda. That is the vector, so you have to divide by 0.375 squared plus 0.75 squared plus 0.75 squared. Okay, this works out to be 1.125, and this works out to be the F when you actually plug in all the numbers, 450 divided by 1.125. It ends up being a nice even number, 150 in the I, plus 300 in the J, minus 300 in the K. Okay, so now I've defined my force. So now I just need to simply do the R cross F. So moment at A is R cross F. I, J, K. R is 0.5, 0, 0, and 150, 300, minus 300. Okay, is I is going to be 0 times 0, so 0, minus J, so this times that, so minus 150, plus K times 150. So therefore the moment at A is 150 in the J direction, please write, plus 150 in the K direction. Okay, so that is the moment vector here. And so if I was to sketch that out, what do I get? So 150 in the J, so equal in the J and in the K, so it's coming off like in that direction or something like that. That is my moment vector. Okay, but that moment vector, it's a vector, right? It has components in all sorts of different directions. And what do I care about? I just care about the portion of it along this axis. Because again, why? Because that's what we're saying. Knowing the tension, determine the moment about the diagonal AD so it's all that matters is along that axis. So therefore, how do I do that? Well, if I want to know any portion of a vector along another vector, I use the dot product, right? So I'm going to say the moment, I don't know, along AD, and notice it's a scalar at that point. So it's not a vector, it's a scalar, is a moment at A dotted against the unit vector. So lambda from A to D. Okay, so let's define lambda A to D. Lambda A to D is, so it goes 1 I, 0 in the J, and minus 0.75 in the K. But remember, that's the whole vector, so I need to divide that by square root of 1 squared plus 0.75 squared, which is what, 1.2525. So therefore, lambda from A to D is 0.8 in the I direction minus 0.6 in the K direction. There's and 0 in the J direction. Okay, so then now I take my moment vector and I dot it against this right here. So the way I often do this, if it'll let me scroll up, which apparently it's not. What do you do? Yeah, look at that. I will win. I think it just went back to where it was. Anyways, so I'm going to say the dot product, so moment of A dot against lambda A to D, okay, is I'm going to say 150. So actually I'm going to do 0 in the I plus 150 in the J plus 150 in the K. And here I have 0.8 in the I and 0 in the J and minus 0.6 in the K. So then you just 0 times this is 0, this times this is plus 0, and you end up with, what is it, 90 in the K direction. Sorry, I forgot a negative sign. That's minus, nope, cut it out. Minus 90 in the K. Sorry, not in the K. Whoa, because the I dot I is 1, J dot J is 1, K dot K is 1. So it's just minus 90. So therefore, the moment from A to D is 90, what is it, Newton meters? So it is a scalar, because again, we're talking what fraction of the moment vector is in that direction, and there's 90 Newton meters in that direction. And that is the answer. So the key here is this, is that you think about this. You could do it with a triple product. If you think about it, all a triple product is doing is this replacing these right here with this. So what does it end up being like? Let's see if I can write this. 0.8 and 0 and minus 0.6. And so mathematically it's the exact same thing. It works out to be exactly the same. I don't know, I just like thinking about it this way, that you're finding a moment vector and then you're saying how much of that vector is in some given direction. You can think about these, there's all sorts of examples. The most obvious example is a door hinge, right? That when you pull on a door, presumably your hinges are strong enough that they're just going to prevent you from pulling the door off the wall. So all that you really care about, you're producing a moment on the door. Part of that moment wants to pull it away from the wall, part of it wants to rotate it around the wall, and part of it wants to open and close the door. And assuming that your hinges are strong enough that you're not going to do any damage, the only thing that you really care about is what portion of that moment opens or closes the door. It's the same idea here. What portion of this moment that goes in multiple directions has any meaningful effect? And that is the answer.